what the laws do. So this one's called the product rule. Product means multiply. That word product means multiply. So when we have two bases that are the same, what happens with the exponents is, like an x times x, we add the exponents. So for example, 2 to the power 3 times 2 to the power 4 would simplify to 2 to the power 7. Okay? Same base, add the exponents. Questions? It's very theoretical, right? It's where the math gets. Let's do product rule. Let's do another example. So I'm going to add something else to it. And by the way, is anyone Is anyone surprised that 2 to the power 3 times 2 to the power 4 is 2 to the power 7? Does that surprise anyone? No, good. Nadia says no. So it shouldn't, because let's just quickly, before we do another one, I just want to show you something. And you can do this yourself if you ever get stuck on a... Okay, we add the exponents when you're multiplying the same base. Because what does 2 to the power 3 really represent? 2 times 2 times 2, right? What does 2 to the power 4 represent? Right? So if I wanted to write that shorthand, I'd write 2, multiply it by itself, 1, 2, 3, 4, 5, 6, 7, 7 times. Right? Okay. So the product rule, let's get a little trickier though. And same with x's, right? Like if I had x to the power 3 times x to the power 4, I'd have 7 altogether. Let's try this. What if I had 3x to the power 4 times 2x to the power 2? Okay, what do you think the answer is going to be?
6x to the power 6. 40.
How many x's do we have, by the way, altogether?
5 or 2.
4 and 2, 6, right? X to the power 4 times x to the power 2, I add the exponents, I get 6. And 3 times 2, when you're multiplying, the coefficients multiply together just like numbers normally do. 3 times 2 is 6. So the answer would be 6x to the power 6. Okay, are we okay with that? Stop me if you're not. But you can reference, so coefficients, when you have coefficients, those numbers attached to the letters, they multiply or divide just like normal. You only have to worry about those variables, right? So how do we do with variables? Well, this chart can tell you what to do with the variables. If I'm multiplying x times x's, I just add the exponents together, right? Let's do one more. What if I had negative m to the power 5 times 4m to the power 12. If I told you to multiply these two monomials together to simplify, what would you end up with? Negative 4 is the coefficient, right? And how many m's do we have altogether? Yeah. Okay. Let's do quotient rule. Now, quotient means there's division involved. And we know, and we've learned, that multiply and divide are opposite operators to each other, right? They undo each other. So it should make sense if I'm multiplying the same bases and I add the exponents, what do you think you're going to do when you divide the same bases? Yeah, if I have x to the power 10 over x to the power 6, I'm going to subtract the exponents and I'll be left with x to the power 4. Right? If I do a simpler one, which I should have done right away, if I have x to the power 5 over x to the power 3, what's the simplified polynomial going to be after I do the division?
How did you get that x4?
Let me show you here. Following that rule, Cliff, what would this one be?
I don't know.
Well, what does it say up here? What does it say with the exponents? A minus B. Subtract the
Oh, okay.
exponents. And that's because, how did I get that? Well, remember what x to the power 5 is? How many x's are there? 1, 2, 3, 4, 5. And if I had 3 on the bottom, now remember how division works? If I have the same thing on the top and the bottom, they can cancel each other out, right? Like an x on the top and x on the bottom would cancel each other out. So I'd be left with 2 x's, x to the power 2. We've got some more examples to do in the book too. Okay, what about the power rule? Let's take a look at the power rule first. Darian? What does the power rule say? The power rule says, look at this one. X to the exponent A to the exponent B is x to the A times B. So if I have, in a numerical example, 2 squared cubed actually simplifies to 2 to the power 6. So we multiplied the exponents together. Can you see that? So when you have an exponent on top of another exponent, they get multiplied. So let's see why that is. Well, let's take another look. What if I have x to the power 3 to the power 4? Okay? What will be the simplified answer?
x12.
X to the 12. And the reason for that is, I'll just show you, x to the power 3 is going to be what? X to the x times x times x, agreed? 4 times, I'm going to have 4 sets of these. X times x times x, x times x times x, x times x times x, if I'm going to show you completely. So I have 4 groups of x times x times x, all together 3, 6, 9, 12. That's why it becomes x to the 12. Okay. How many of you is this like a repeat for? No? 1? How many is this sort of kind of newish? Okay, good. Glad we're going over this again. I think I'm going to leave negative exponents for now, and I'm going to tell you why, because we don't deal with negative exponents in polynomials, but now you'll see why. Remember when we were trying to decide if something was a polynomial, and I said there could be no exponents on the bottom? This is why, because if you end up with an exponent on the bottom, it's really a negative exponent. So I'm just going to shelve that for a sec. This is worth knowing about, I think, just in anyone's math career. This was just come to by convention, by the way. It's kind of hard to prove this in a way, but the exponent of 0, anything raised to exponent of 0 is 1. So that's kind of cool. It is strange, right?
So if you can't have an exponent on the bottom, so we have quotation rule that says more examples of polynomials. Is it a polynomial then? If you said you can't have an exponent on the bottom?
Correct. It's not a polynomial.
Okay,
So this would not be a polynomial. You're right.
so it's not exactly.
That's true. Actually, I didn't put a polynomial down here with that. Oh, no. This is a polynomial. You know why?
Okay.
Because it ends up simplifying to x to the power 4. Right? Because there were more exponents on top than bottom, so it actually did simplify to a polynomial. But that's a good question. But not all the ones up here are polynomials, right? And they're just the exponent laws. Because sometimes you are dealing with exponents, like there's other worlds of math that don't involve polynomials. These exponent laws apply to those other worlds of math. So, and that's the reason I said we're not really going to talk about this because we're just talking about polynomials. So we won't do that one. But the exponent of 0 is interesting, like 0 exponent. It doesn't matter what you have. Like for example, let's say I had, I don't know, like 1,572, x to the power 11, y 13, z 45. But they were all bracketed off inside and they were all raised to exponent 0. That just equals 1. Okay, an exponent of 1, well, I guess that's pretty self-explanatory. I think you guys probably are okay with that one. Anything raised to the power of 1 just remains itself, like 5 to the power of 1 is 5. Okay? Okay. So that's your handy little law of exponents. And this, yeah, you can use this for your further math career too,
Why
right?
wouldn't it be 5 times 5, since it's just got a 1 there?
Well, 5 to the power 1 means there's only 5. That 1 means there's only 5 present. If it was 5, if you want 5 times 5?
It'd be 2?
Yeah, it would be 5 to the power 2, right?
So you wouldn't see that either then, very often, right?
What do you mean?
With an exponent of the 5? 5 to the power of 1, you wouldn't really see that, right?
Why not?
Because it's just 5, right?
5's a nice number. Why
I
wouldn't
know,
you
but
see
why would
5?
they use that though, you know? 5 to the power of 1.
Oh, I see, because it's so simple.
Okay.
Is that why you're
Yeah.
asking me? Yeah, yeah. They're just getting the point across that anything to the power 1 just remains itself. I see what you mean, right?
Yeah.
I probably wouldn't use the word like 5 squared that much. I would probably just say, oh, it's 25, if that's what you mean.
Yeah.
Okay. Okay, let's just take a look. Now let this simmer a little while. We could do a little more with exponents too if you're kind of interested in this kind of stuff, and I can show you in more depth why exponent 0 is 1, if some of you are dying to know. Yeah? Okay, well okay, I'll come talk to you later then. If anyone else wants to come, we can talk more about it. Because it's kind of fascinating, right?
Yeah.
Sometimes in math and science, things are just decided on by convention, but other times it's just because it's proving by induction, just by proving following patterns, that it has to be. It has to be so. So let's take a look at I'm on page 12. And we're just talking about multiplying with multiplying polynomials. So we're going to do a little bit of multiplication today. Now this easy stuff should be straightforward, I think. They get a little more involved, right, than just x times x. So this should be, it says multiply the following polynomials. So far, all we've done with polynomials is add and subtract. Agreed? We haven't done multiplying or dividing. So today we're just going to concentrate on multiplying. So now you know there's an easy way to do this. X cubed times x to the power 4. I would multiply, and that would give me a product of x to the power 7. Agreed? Okay. Remember, brackets indicate multiplication. So I have 3m to the power 4 times m squared. There really is a coefficient here, isn't there, on the m squared? What's the coefficient of the m squared? 1, right? So 3 times 1 just remains 3. How many m's do I have? 6. Okay. 2 negatives multiplied together to give me a positive, so I'd have a positive 2. I have x to the power 5, y to the power 6. Okay, next one, record your answer. Record your answer for the next two, for D and E. Okay, answer to D. Anyone want to call out to B?
-12,
Mm-hmm.
3, Q8,
Yep. Negative 12 p cubed q8. P to the power 3 q to the power 8. Yeah. Okay, the next one, you've done this before. It's involving a fractional coefficient. So we have to multiply with fractions again, right? So you might kind of want to move to the side or move to, and just show your multiplication of coefficients. I've got -1/3 times -9. What do I do if I have a fraction mixed with a whole number? Yeah, it's really 9/1, right? So I get a positive 9/3, right, which is just 3. So your coefficient would be +3, and then I have m to the power 9. I have 9 of them all together, and I have 6 n's, so n to the power 6. Okay.
On C and D, where'd you get the 3 and the 5 from? Like x to the power of 5, or?
Where am I?
On C?
C?
How did you get a 5 out of that?
They just put a 1 beside the x.
Yeah, if there's no exponent visible, it's a exponent 1.
Oh, okay.
So 1 and 4, because there's an x here, right, Cliff? There's no doubt that there's an
Yeah,
x.
yeah.
So I have 4 here, 1 here, there's 5 altogether. Right? And then 3 y's and another 3 y's,
You're
total
adding
to
because
6.
it's multiplication.
Correct. Yep.
And you're adding the y's to, oh yeah.
Okay, now let's try, this was, if you read the instructions, because the instructions are informative as well, multiplication with monomials. Remember, monomials are just polynomials with one term. So we did one term times one term, mono times mono. Now we're multiplying a monomial with a polynomial. That means it's going to be bigger than one term. So when we multiply monomials with polynomials, we multiply each term in the polynomial by the monomial. We call this the property of distribution. Okay? So what that means is, let me do a really simple distribution, maybe a really simple one. Like if I have 3 times x plus 4, for example, monomial times a binomial, what it means is 3 is being multiplied by each piece in the bracket. So 3 times x results in just 3x, we call it. 3 times 4, 3 times a positive 4, both positive, is a positive 12. So then you're done. That's what multiplication is. Multiplication involves removing the brackets, right? Because the brackets are indicating multiplication. So basically, if you could understand what we did in example 1, here you're just doing that process 3 times, right? I think the first thing I would do, though, is I'd reach back and remember BEDMAS. BEDMAS always says look inside the brackets first to see if there's anything you can do. That usually makes your job easier. So I'm looking inside the brackets to see if there's like terms. I think the way this example was set up that all the like terms have been combined. But let's just quickly look. I've got a cubed, a squared, a. None of these are like terms, right? So I'm just going to go ahead and multiply. So 5 times 2 gives me 10. And then I get a to the power 4. Now, there's nothing to multiply the b squared with, right? So it just remains b squared. It just stays like that. The next coefficient will be a -15. And I would have a to the power 3. And again, there's no b's, so it just remains b squared. Then my final term will be a positive 35. There's 2 a's, a squared, b squared. Okay? And there's so many a's and b's in here, but none of them are alike. None of the terms are like terms, so it just has to stay like that. So that is my final answer. Questions? No? Yunesa? No? Okay. All right, let's try the next one. Look inside the brackets, no like terms, but it's a trinomial again. So I'm going to have negative 5x cubed, positive 20, x times x, that results in x squared, right? Negative 5x times 1 results in negative 5x.
How'd you get negative cubed there? 5 cubed. Negative x.
Negative 5 times 1 is negative 5, right? I have x to the power 1 here, and I have 2 here. 2 plus 1 is 3.
Oh.
Same question as before, right? Yeah. Questions from anyone? Is this example C? Coefficient would remain 5, right? X squared times x squared gives me what? Jordan? Yep. 5 times negative 4 gives me negative 20. How many x's do I have in total? X cubed. I have 2 here and 1 here. And then this last one is positive 15, and it just remains x squared, right? There's squared here, no x's here, so I'm just left with x squared. All right, I'm going to challenge you to try the next one on your own first, D, because it involves a fraction. So it's good practice with fractions. You've got to multiply an eighth by 4, and then an eighth by 16, and then an eighth by 1. So see what you end up with. What do you mean by reduce? Yeah, if you have fractions, always reduce fractions if you can. Okay. Who got an answer? Anyone want to share? Vanessa, what'd you get? 1 out of 4x squared. Let me record this. 1 out of 4x squared. Okay. Anyone agree or anyone get something different? I agree with most of this. Not all of it though. Yeah.
Would that be a half?
And then everything else the same? Who agrees with Jordy? Anyone agree with Jordy? Anyone got a different answer? Okay. I think I agree with Jordy. Let's see. So first of all, when I'm multiplying 1/8 times 4, right? 1/8 times 4, that's 4 over 1. So it would start off like 4/8 x squared plus, same thing, 16/8 plus 1/8. And if I was going to do lowest terms, 4/8 would be 1/2. So 1/2 x squared plus 2x plus 1/8. So I agree with Jordy. Okay, next one. I would have negative 2xy times the x. Well, the negative 2 just stays as a coefficient negative 2. X times x becomes x squared. The y just stays. There's nothing to multiply with. Then I would have a positive 6x y squared minus 20xy. It was almost just being, that one just almost involved just multiplying coefficients together, right? All right, last one, it's involving a decimal. If I told you didn't have a calculator to use, do you think it's easier multiplying this in decimal, or what's 0.25 in fraction form? 25/100 or 1/4, right? Is it easier for you to look at it like this? 1/4 PQ times 8p squared q squared minus 12? So you're multiplying 1/4 times 8, or 1/4 of 8. What's 1/4 of 8? 2, right? So 1/4 of 8 is 2. I'd have p cubed q cubed minus, well, what's 1/4 of 12? 3, right? PQ. There, you can do it that way, right? Okay, I feel like I'm torturing you, but how about working on assignment 3? I'll assign that to you. I also have some stuff to hand back to people, so that's all I'll do today. Work on assignment 3. Catch up on anything that you've been letting slide, maybe, if